We consume some part of those harvested power to relink the tethering it and start another pumping cycle. The aircraft can be in a rigid and soft kite, and it is important to have a model for the optimization and controller purposes. Two types of the models that is usually used is a minimal coordinate and non-minimal coordinates in the literature. In Gross and Gales in 2013 compared these two kind of the models. The minimal coordinate uses the Euler angle or quaternion representation, while in the non-minimal coordinate we have a direct cosine matrix representation. So in a minimal coordinate, the system, the model is more nonlinear and non-diagonal, while in a non-minimal coordinate is less nonlinear, but higher the number of the states is available there. And lastly, there are possible singularities in Euler angles, while in a non-minimal coordinate, there is a non-singular parameterization. So Gers and Deg conclude that non-minimal coordinate is more preferred for optimization purposes. But the wing itself is not the only part of the airborne wind energy system. There are plenty of options, there are plenty of studies have been done to model the tether itself. For example, the simplest one is considering tether as a rigid rod. So in this case, we add a constraint to the dynamic. And other type of modeling is assuming some lump masses on the tether. So another is a quasi-static approach. So for example, we consider n lump masses on the tether and connect it with the n+1 spring between them, and we use for example, algebraic equations, some shooting approach in each time interval in our solver. And finally, we can consider a fully dynamic for each long masses on a tether, which can add a 3 degree of freedom to the tether model. Typically, the more accurate model we use, the more computational effort needed. So from the optimization point of view, it is really it's a trade-off between the it should be a trade-off between the accuracy and the computational effect. So, but a model with a flexible tether has some benefits, some features indeed. It has a smaller stability region compared to the rigid one, and we can predict the drag force a little better when we consider a flexible tether in our model, and we can avoid scenarios such as a tether ground contact and tether aircraft contact when we model the tether as a flexible one. Consequently, it can be used in optimization for a better power estimation, and we can use these kind of models for a better involvement of retraction phases in the optimization problem. In terms of the path planning, typically two kind of passes is used for the flying aircraft, the lemniscate and the circular ones. Typically, the lemniscate passes is preferred for soft kites due to the it doesn't cause twist in a tether. But while we are talking about the path planning, we are talking about finding the states, optimal states, and control inputs to for our system. Here you can see two optimization. Two optimization has been done in the literature for a circular and lemniscate passes. We are going to minimize this cost function or maximize minus this function subject to the dynamic and subject to the inequality and equality constraints. As you can see here, I wrote the dynamic of the system in form of the DAE format because in these two works uses a DAE format of equation. with considering the rigid tether as a rigid rope. You can see here how elevation angle decreases with the increase of the wind speed in a differential work. So, and megAWES, almost all of you know about the megAWES. Unfortunately, Dylan is here, someone who developed the megAWES. It flies in a pumping cycle. It consists of the aircraft, AMPX 84, which is upscale of the AMPX 83, right, in a megawatt order, and uses a minimal coordinate and Euler representation, while uses a static aerodynamic coefficient. Typically, the using Euler representation is less preferred in optimization purposes, but presence of the, and there is a range, of course, 1 degree of freedom for every inch. But the presence of the quasi-static method in a tether make me interested about implementation of the optimization approach to the megAWES. But the megAWES itself has a controller and a path planning scheme. According to the Sebastian Grab work, it tries to track a lemniscate of the boost over a unit sphere. And it also has a covariance matrix adaptation evolution strategy optimization method. Here, this kind of optimization method is different from what I'm going to talk about today. Because we are in this kind of optimization, Dylan optimized the controller parameters and the parameters of the lemniscate of the boost, the path itself. But I'm going to use direct multiple shooting. Direct multiple shooting is one of the most popular approaches in a path planning, in which we are going to discretize the states and control inputs over the time into the smaller subinterval, which means dividing the time interval into the a smaller interval or shooting interval. And we are going to impose a continuity constraint to the system to make the final path should be continuous, and also some periodic constraint to make our flight continuous, and as well some inequality constraints. So the question is, why should megAWES be used in the optimization problem? Okay, the model itself is in a minimal coordinate, which is less preferred for the optimization purposes. But the answer is that I'm going to address a reality gap in the optimization process. You know, almost every research in the optimization of the path planning of the airborne wind energy system uses a rigid rope, a DAE format of equations. So there is I couldn't find any higher fidelity model for the tether, and I wanted to know how it could be. So let's talk how. In order to minimize these cost functions subject to dynamic and continuity constraint, it is necessary to discretize the paths. You can see here the discretization of the paths for the lemniscate and circular passes generated by the megAWES. As you can see, the aircraft here shows the position of the aircraft at the end of each shooting node. Here, I mean, the aircraft at each plot is the states and the control input is at the end of each shooting node. So for a complicated model like a megAWES with 14 states and 5 control input, if we just discretize model into 21 shooting nodes, we have 294 optimization parameter for the states and 100 optimization parameter for the control input. then this is for the simplest form of the control, I mean the zero order hold, if we consider the control input as a zero order hold at each subinterval. Fortunately, since we are going to use quasi-static approach, we are not going to consider 15 lump masses on the tether. We are not going to use these 15 lump masses into optimization problem, which means we are not going to, in these 15 lump masses could have imposed 19 states to the dynamic, and consequently for a 21 shooting node could have imposed 1,890 optimization parameter, which could have made the optimization problem unfeasible, and these parameters are quite absolutely unnecessary. So we try to use a more complicated model for a tether in an optimization parameter, in an optimization process, while we are not going to add those dynamic to the optimization itself. But it is a little bit challenging because there are some singularities, and we have a performance problem, we have a singularity problem here. The singularities problem arises from the numerical calculation in a tether solution. The dogleg method uses for the quasi-static approach in the tether dynamic converge to unreal values sometimes, and sometimes it didn't converge at all, because it is the optimizer tried different contribution of the values for the different type of values for the states and control, which lead us, which cause the singularities in the tether dynamic. Of course, in a numerical solution of the tether. And also there was some singularities related to the Euler because of the minimal coordinate model of the megAWES. And in terms of the performance, megAWES was developed in a Simulink, and Simulink is more computational demanding compared to the other programming languages, or even with an M5. For example, if implementing direct multiple shooting for a simple model like a van der Waals oscillation in a Simulink environment could be 100 slower than in M5. So, which is less preferred for the optimization, of course. And there are some discontinuous lookup tables there. So we couldn't calculate gradients for our, we couldn't provide gradients for our optimizer. This was the second drawback. And lastly, there are plenty of due to the complexity of the model, we have plenty of optimization parameters. So to tackle these parameters, these problems, firstly, I performed some modification in a objective function of the tether. Indeed, I understood that the dogleg parameters didn't converge due to the singularity of the gradient inside of the dogleg, because the gradient function was too close to zero. And I understood that when I replaced the dogleg method of implemented by the Dylan with the MATLAB fsolve function. So into the through the log, I understood that the dogleg, the gradient function inside of the quasi-static approach is too close to zero, and this is why it gets unstable. So in order to tackle this, I update the objective function inside the tether dynamic. I mean, the objective function was the difference between the last point on the tether and the kite. So this value, the gradient of this cos function respect to the initial guess at the range, I guess, the direction and attitude of the fourth tether was close to zero. So I just multiply this cos function into an integer. So it is it skip. They optimize in the optimization process. It can be saved, and the non-singularities actually disappear. And in terms of the constraint, I also add some constraint for the tether.
Need to finish. Your time is out. 15 minutes.
Okay then. So in terms of the Euler representation, I just limit Euler angles. I use a quaternion. And finally, in terms of the optimization, I just converge to the M file. I move the model developed in the Simulink. I move to the M file in order to be able implement direct multiple shooting there. And I replace these continuous Lookup tables with the polynomial expressions. I feed the polynomial that can be used for the gradient. And in terms of the higher number of optimization parameters, it is necessary to calculate gradient. And this is the stage I'm working on. Because calculating the gradient is a little bit challenging. Because the tether dynamic, although the tether dynamic is not added to the optimization parameters, but should be, the effect of the tether should be considered in calculation of the gradients. Here you can see an early stage of result on the right for 320 shooting nodes, and it's too slow due to the finite difference gradient there, and it took time to calculate this. This is why it is necessary to calculate, to supply gradient for this optimization problem. So I addressed the optimization method direct multiple shooting for megAWES MPCM4 and to fill in the reality gap of lack of complicated tether for the in the optimization and path planning. So the problem size remains reasonable, but there are some challenges related to the performance and singularities that should be addressed and tackled. And I introduced some methods and techniques I use to tackle those difficulties. Thank you for your attention.